I'm just going to do a quick derivation to help you understand how we can derive different equations from Newton's second law and Newton's universal gravitation related to circular orbits. So I drew a sketch of a planet with radius capital RP from here to here, from the center to the surface, and then a satellite in a circular orbit around the planet at a height h. Not to scale, obviously, pretty rough drawing. Remember that Newton's universal gravitation is capital G, m1, m2, the masses of the two objects multiplied by each other, divided by the radius squared, where the radius is the center-to-center distance. So that's the entire distance from the center of one object to the center of the other. Remember that when an object is moving in a circle, we can use Newton's relation for net force, mv squared over r, and if necessary, we can treat the speed v as the path of the circle, 2 pi r, over the period, the time for the object to make a complete circle. So remember that if the object is moving in a circle, it must have a net force towards the center of the circle. For this satellite, the only force that's available to provide that net force is the force of gravity of the planet on the satellite. So that's the gravitational force of the planet on the satellite. So then, in order to find the orbital speed in a different relation than this, we can apply mv squared over r and set it equal to Newton's universal gravitation. So that would look like this. But the two objects that I have, I need to distinguish between them. I'm going to be a little more specific than m1 and m2. We'll call this the mass of the satellite. And then here, let's erase this lowercase m. A lot of times we use an uppercase m for the larger object, and we'll call that p. We can just leave this r squared and r for now, but we can later substitute in these. So first thing I want to point out to you is that the mass of the satellite doesn't matter. It's on both sides of the equation. So we just divide that out. And now we have v squared over the radius equals the g constant times the mass of the planet over r squared. Next thing to notice is that one of the r's divides out. So now we have v squared equals g mass of the planet over r. We can take the square root of everything and have an answer. And we can go ahead and substitute in the two dimensions that I put on the diagram and have a more specific answer. And there you have it. We found an expression for the speed of the planet, of the satellite around the planet, in terms of a constant of nature, the mass of the planet, and the height of the orbit, the distance of the orbit from the center of the planet to the center of the satellite. Thanks for watching. Remember, what one fool can understand, another can.